Alright, today we are going to go over how to solve quadratic word problems. One of the things I want you to make sure that you're paying attention to is what the questions are asking. I have a typo on this first slide, so let's go ahead and edit that before we start talking about anything else. In front of V sub 0, we need to change that to a plus sign. I got in a hurry when I typed that and just missed a button. So those should both be plus. So just real quick, don't want to get into too much background, but anytime that an object is dropped, launched, thrown, hit, shot, as long as it's not guided or acted on by anything else, we're going to use these two position formulas, and this is called projectile motion. And so these formulas give us the vertical height of a object as time passes. And it goes through and it explains what each one of these variables stand for. Big thing to pay attention to is for this initial velocity. Sign is important on this. If it has an upward initial velocity, it would be a positive for an upward initial velocity, and if it's a downward initial velocity, then that is going to be a negative. So just watch that as you plug it in. And then whenever I'm working on word problems, I like to try to do two things. I like to try to draw a diagram of what the situation is, and then I like to sketch a graph and see what the concept from a graphing standpoint looks like. So we're going to kind of quickly read through this. After the semester is over, the math department has changed textbooks, so the bookstore won't buy your new book back. You and your friend Herman decide to get creative. You go to the top of a 12-story building. You look over the edge to the 160 feet below you, and then you drop your book over the edge. At the same instant, Herman chucks his book. So what we're talking about is one object being dropped and another object being chucked or thrown straight down at 48 feet per second. So as we're going to set this up, we're going to start by making just a quick sketch of what you would observe if you were standing by and watching it. So if this is the ground, and then we had our building, you would have two people up here on the roof, you and Herman, and then you'd have two books. Both of these books are falling vertically straight down. So what we're looking at when we're looking at this particular picture is this is the height of the object. Okay, it started at 160 feet. One of the things we want to label right here is the fact that this says 160 feet. Okay, one object is being dropped, the other object is being thrown, so the object that's being thrown is going to hit the ground faster. So that's just the background of what's going on. So and the reason why that's important to think about is we're going to come over here to the left side of our page and we're going to sketch two graphs. One sketch that represents you and your book, and the other graph that represents Herman and his book. Okay, so the thing that's different about quadratic drawings than other things is as we're thinking about this setup, our y-axis is still going to be height. So our y-axis is still the height of the object. But what's unique about quadratics is, or not unique about quadratics, but what this situation is modeling is not this. The x-axis is not the horizontal distance the object is from the tower. This is the amount of time that has passed. So both of these are time. And that's really important for you to keep straight because we want to make sure that our graph models the situation, the mathematical relationship, and doesn't match necessarily the diagram or the picture of what you would observe if you were watching this. So a couple of quick things. Number one, since we're standing on top of a building, 160 feet off the ground, before any time passes, when our t is 0, then that's our y-intercept. And both of these objects had the same y-intercept. So we're going to graph those, and we're going to say that that is 160, and that is 160. The next thing that's going to happen is the object is going to fall. And this is just something you have to know a little bit about objects in motion. If objects drop, they gain speed as they fall. So it's not a linear relationship. It starts out falling kind of slowly, and then as you get closer to the ground, the speed picks up, so it gains more distance. And when we look back at our formulas up here, you'll notice that in these two formulas, they're both squareds, so they're both quadratics. So that's the representation of yours, and then Herman's is going to do something similar, but Herman's falls faster. And because Herman's falls faster, his graph is steeper. And because his graph is steeper, he's going to hit his time sooner than yours. So those are the two models. And now we're going to go back and we're going to look at the word problem and make sure that we know what we're solving for. So we read the word problem again. We're identifying some key information. And then it says in this paragraph, in this sentence right here, about how many seconds does his book beat yours to the water. So what we have to remember is the water is the ground. And the height of that object when it hits the water is 0. So what we're talking about on these quadratics is we're really wanting to find when is the height 0. And the math concept behind that is we're looking for roots, we're looking for zeros, we're looking for x-intercepts. And those vocabulary words, remember, are the same thing. So we're going to find your root, we're going to find Herman's root, and then we're going to find the distance, the difference between those two times, and that's what this question is asking us to do. So what we do real quickly, we go back, we look at our formula. Since they give us feet in the word problem, since they give us feet and feet, we're going to use the one that says feet. And so we're going to quickly copy it. We're going to copy our quadratic down, and for yours, it's h of t equals negative 16t squared. Because your object was dropped and not thrown, then our initial velocity is 0. So plus 0t, and then we add our initial height. Our initial height is 160 feet, and notice this c then becomes our y-intercept. So that's one of the beautiful things about using standard form, is standard form we can find our y-intercept by looking at our constant term at the end. So from here, we're going to look and we're going to double check what our concept is, and we're solving for our 0. So we're going to set the height equal to 0. And then as we rewrite it this time, let's consider that we don't need our b term because 0 times anything is going to be 0. So we can simplify this and we end up with this quadratic. From this point, you have lots of different ways that you could solve this. And as I've told you all before, if this is a quadratic and we're setting our quadratic equal to 0, you can always use the quadratic formula for this. So if you don't want to think about different strategies, if you just want to do it the same way every time, then you could always use your quadratic formula. But what I think is kind of easier to do in this situation is look at your numbers. When we look at this, we realize that both of these have a 16 that we could divide out. So again, with most of math, at this point in high school, we need to start looking for GCF. So let's make these numbers smaller so that we don't have to rely on calculators to do the work for us. So what we're going to do here is we're going to divide both sides by negative 16. And then when we do that, we get 0 equals, and we use the negative because our leading coefficient here was a negative. So that would be positive t squared and then negative 10. Since we're missing our b term, then there's an easier way to solve this than the quadratic formula, and that's solving by using your inverse operations just from regular algebra skills. We're going to add 10 to both sides, and that gives us 10 equals t squared. So then to solve this, we're going to take the square root of both of those. When we take the square root, we get t equals a positive square root of 10 and the negative square root of 10. So those are our two solutions. Consider the fact that our input is time, and since time cannot have a negative, or even if it could, we don't know what this object did in the past, so we're going to ignore the negative answer and we're only going to work with the positive answer. Because we have not yet answered the question, we're going to leave this square root of 10 as an irrational root. We're going to leave it how it is. That way, if we need to use it later on, we don't have to recopy a bunch of decimals over and over again. So we're going to leave it like that. We're going to move on to Herman's. Herman's formula is h of t equals negative 16t squared, and his is going straight down at 48 feet per second. So because his object is getting thrown downward, it has a negative initial velocity of 48 and then times t, and then he had the same starting point. So from here, we're doing the same thing. We're going to set Herman's equal to 0. And then as we look at this, we notice that we could factor out the same negative 16. So that gives us 0 equals t squared plus 3t minus 10. At this point, again, we have lots of different strategies. We could use the quadratic formula. We could use completing the square if we wanted to. A student actually asked that question today, and I said, yes, you can use completing the square, but because 3 is an odd number, when we divide that 3 in half, we get a fraction, and we'd have to carry fractions all the way through our problem. So this one might not be a good one to use completing the square on. Let's look to see if we can factor this. So when we go to factor this, we think of what numbers multiply to give us c, and add to give us our b term. And our b term is 3, our c term is negative 10. So that would be negative 1, positive 10, or negative 2 and positive 5. When we add those together, this one equals 3. So those are our factors. So we're going to factor this. So t minus 2 and t plus 5. And then using our zero product property, tells us that if either one of these parentheses can be set equal to 0, then the whole equation would be equal to 0. So we're going to go back and we're going to solve this twice. T minus 2 equals 0 and t plus 5 equals 0. Okay, the t minus 2 equals 0. To solve that, we add 2 to both sides, and that gives us t equals 2. And here, when we subtract 5, we get a negative time again, so we don't need that one. All right, so Herman's book took 2 seconds to fall. Your book took square root of 10 seconds. Okay, so 10's not a perfect square, but 9 is a perfect square. So the square root of 9 would be 3. So your book took a little bit more than 3 seconds. Herman's book took a little bit more than, or took right at 2 seconds. So to find out the difference between those times, we're going to do your book, square root of 10, minus Herman's book, which is 2, and we end up to the nearest 100th. We end up with approximately 1.16 seconds. Okay, so that's how we would work one out. Now this one's more difficult. There's more steps, but go back to your drawings, go back to your graphs, and then work it out, looking at the concept that you're solving for. So because we were looking for a root when our height was 0, we set it equal to 0, and we could use quadratic formula. We did a GCF out first. We solved it by hand. For this one. Then the one down here at the bottom, we factored this one. So, I mean, there's lots of different ways. Just remember, if you ever get stuck and it's a quadratic, you can always set your quadratic equal to 0, find the root, and then that would tell you your intercepts. Okay, now that might not be the right question, but if it's asking you for when your height is something, when your output is something, set it equal to the output, move that output over with subtraction, and then you can always use your quadratic formula.